Okay, so let's get started. The key or the answers to the 4 questions in the exam, that's actually covered in one of the YouTube videos already. I uploaded it earlier today. No, I uploaded that on Tuesday. So it's already up there, since Tuesday, because we went to the lab and then I explained the answers to the 4 questions. So you can just watch that. If you have any additional questions after watching that YouTube, we can talk about it in the class. Okay, is that all right? Okay. So what we'll do today is we'll continue to focus on local variables, parameters, and returning a value from a subroutine. And then after that, we'll go ahead and start on data structure. Okay. So are there any questions before we continue with these topics? Especially with the homework assignment, are you guys getting started with the homework assignment? Okay, well, this one may take some time, so I suggest that people get started earlier, because this is the first homework assignment where you're messing around with the stack. And when you're messing around with the stack, moving the stack pointer and changing the stack pointer, the probability of getting a segmentation fault is much higher than all the previous programs. So you got to be careful when you do when you're writing programs like this. And the debugging technique is also a little bit different. When you get a segmentation fault, what do? Right? Okay, well, the good thing is if you get a segmentation fault when you're in GDB, you still have access to your registers. In other words, you can still look at your EBP, your ESP, and a few other things that might give you a clue of why you crash, or where it is crashing at least. So there are certain techniques that you can use in this type of program that you may not use in previous programs. And that's why I think it's important to get started early, so when you encounter these problems, I can come take a look at the program. All right. All right. So last time we talked about the frame pointer. The frame pointer is essentially a snapshot of the stack pointer upon entry into a subroutine. Okay, it's a snapshot. Now the nice thing about the frame pointer is once it is initialized within an invocation of a subroutine, it doesn't move. You can have push instructions, you can have pop instructions. They can change the stack pointer, but they won't change the frame pointer. Yes. I believe so. I think I just did that a little bit earlier. Yep.
Recording with sound.
That's a better question. And the answer is yes, it is recording from the right channel. All right. Okay, so getting back to where we left off. Okay, when you set up a stack, and I have put some thoughts into how I can do the recording of stuff that I draw on the board. And the quick and easy way to do it is to have a little webcam that sticks out of the monitor, and I just draw it on a piece of paper, and then I can just have another program to display what is on the piece of paper.
Isn't that an Elmo? Isn't that an Elmo pretty much?
Yeah, kind of like an Elmo.
They don't give you an Elmo?
No. But I can just turn a $30 webcam for that purpose too. So that's what I'll do maybe in the next semester. But at this point I can just use a spreadsheet which works out really good too for this kind of purpose. All right, so here's the spreadsheet which I will use as an example to illustrate how the stack is used. And then I'll use just a mousepad for the program itself. So here's mousepad, and I'm going to write a program that takes 2 parameters. So we just use int x and int y, and we'll have a local variable here, int z. Okay. We'll just do some random stuff here. Z gets x plus y, and then return 2 times z. Okay. The actual code is not as important as the layout of memory. And then the next thing we'll do is to look at this C code and then try to figure out how the assembly code is going to look like. I'll write the assembly code first, And then as we trace the assembly code and also from the caller's perspective, we'll use a spreadsheet to take a look at what items are appearing and disappearing on the stack in that process. So I'll just go ahead and write a G function here. And G doesn't do anything except to have its own local variable called I. And then I stores the result of F 6, like that. Okay? And to make it order dependent, we'll just do a subtraction instead of an addition. So this way, if I order these things incorrectly, it won't give me the correct result. All right, so let's start with F here. To convert this into assembly code, I would start with something like this. OEBP gets a 0. It doesn't seem to be necessary because but what this means is the EBP pointer or the frame pointer is always pointing to its own old value. Okay, and that has to do with how a subroutine is written. So this is these are just labels, but I need the labels to help myself remember where do I find the parameters as well as the local variable. The parameters are on the positive side of ODBP, so this means X is old. Oops, I forgot one thing. The return address. The return address is right after. In other words, it has a higher address that is higher than OEBP, and I'll explain. We'll explain why that is the case as I go through the invocation and also the subroutine itself. And then X is return address plus 4, and the Y is X plus 4. Okay. On the negative side, we have one single local variable. So Z is going to be on the negative side of the ODBP, and it's going to be subtracted by 4 because the size of Z, is 4. It takes up 4 bytes. The subroutine itself is just a label F. The first thing we do before we do anything else is to push EBP. In other words, I don't care how my caller is using EBP. My only job is to preserve that, so to my caller it never changes. And then after the push instruction, I can use EBP whatever way I want to, because I'm going to restore it right before I return. Which also means when I write in code like this, I'm going to finish the code program like this first, and then I go back and insert other things in between. The next thing we do is to use a move instruction, move L, ESP to EBP, so that EBP becomes a snapshot of the stack pointer right at that point. And then the last instruction, or the second last instruction before the return, is to reverse this operation to restore the stack pointer, so I'm ready to pop EBP right at that point. And then since I have a local variable in this case, I will also adjust the stack pointer to allocate space for my local variable. And sometimes, most of the time I say lost local variable is Z in this case. So in my code, I just have to refer to last local variable. I don't have to worry that I have to change the program when I have to add additional local variables. So I just say add last local variable to ESP. So this will reserve the space on the stack. And then I can do whatever I need to do inside this program. And as I said, that's not really the most important part, but we'll go ahead and do it anyway. We'll just go ahead and move, let's see. We can move either X or Y. We're subtracting the X, Y from X. So we'll move X into a register, say EAX, and then we'll move, we can do the subtraction. Okay, X is a parameter, which means we have to do something like this. It has to be, because the label X is a displacement or offset of where EBP points to the item that we're trying to access. In other words, X is basically 8 in this case, as a label definition. It simply means whatever EBP points to, if you add 8 bytes to it, if you add 8 locations to it, that becomes the address of parameter X. And that's why we have to use the base addressing mode, because the base addressing mode will look at the value of EBP, treat that as an address, but it will also add X, whatever X is defined to be, to EBP before it does the dereferencing. So once I move that into EAX, then I can do the actual subtraction from EAX. So I do a subtraction long Y EBP from EAX. and then I can store the result, move L EAX into my local variable Z. So these three instructions will implement the assignment statement inside the subroutine. In other words, these three statements will implement this particular line of code. Are we doing okay so far? Okay. And once we have that, we want to return 2 times Z. There are many ways to do this. Since EAX already has that result, I can just do a add EAX to EAX to basically double the value of EAX itself, and that's it. I don't need there's no particular instruction to specify the return value because it is EAX itself. Okay, if you're returning a scalar, something that can fit within 32-bit, EAX, is used, to specify the return value. So just by doubling EAX, at this point, will give me the correct return value. So are there any questions about subroutine F itself? No questions about the subroutine F? Okay. So let's go to subroutine G. Okay. And in subroutine G, I don't even bother to trace, the rest of it. I just want to keep track of how F is invoked. When we call a subroutine that has parameters, you have to push the last parameter first. In this case, 6 specifies the second parameter, so we have to push 6 first as a immediate operand, and then we push 5, and then we call the subroutine F. And after F returns, we have to reclaim those 8 bytes that we use for parameters. And the quickest way to do it is simply to add 8 to the stack pointer. And then, over here, we can just write whatever code to utilize the return value in EAX. Okay, but we'll just go ahead and focus on these 4 instructions. Are we still doing okay so far? In other words, I'm not implementing the entire subroutine G and just focusing on the invocation of function F. So now that we have the assembly code, we'll go ahead and use the spreadsheet to help us understand the layout of these different items on the stack. So we'll keep this part over here, and then use a spreadsheet to basically look at the code. And I want to see if I can display line numbers. Yep, nice, handy. Okay, so this way I can use the line number on one side. And then we can also, that's kind of hard. I think I have to do it a little bit differently. So line number, yeah, it will still work out okay, I think. All right. And the rest would be the stack. So this is how I'm gonna represent the stack. Okay, column B itself, is going to represent the first part, represents the line. And we'll just go to line 39 because we'll start execution from this point. So the line number is line 39, and at that point, the stack would have 6 pushed on the stack. So we have 6 on the stack here. I need a different way to indicate what the stack pointer is pointing at. So I just put a box around this. Okay, so we'll go ahead and put a box around it. There we go. And we'll specify a full border, just like that. Okay, so the border specifies what the stack pointer is pointing at. Now remember, the stack pointer is not really pointing at all 4 bytes that we use to represent 6. It's actually pointing at the lowest byte that 6 is using. Okay, 6 is represented as a 32-bit number, which means it is using up 4 bytes on the stack. The stack pointer is pointing to the least significant byte, or the byte that is at the lowest address. Okay, but for the purpose of this discussion, we can just do it this way. And then we have line 40. So after line 40, the stack will have 2 items, right? It has the original 6, and then plus it has 5 next to it. So the stack pointer will now be pointing at the second item, or the latest item that I push on the stack. So we put a box around this guy this time. So are you guys kind of following, how I'm using a spreadsheet to basically display the content on the stack, after each line of code that I execute in assembly? Okay, so here's line 41. Okay, so line 41, is a call instruction. A call instruction has a built-in push to it. Okay, 6 and 5 are both still on the stack, but we have a return address to G at this point. I'll just call this a return address because we only have one, so we'll just go ahead and call it return address. And this becomes the latest item pushed on the stack, and so the stack pointer will be pointing at this item after line 41 executes. Are we still doing okay so far? Okay. After line 41, we'll continue execution inside the subroutine inside F. So that's why the execution or the line number is no longer 41 or 42, but we are going to line 16, which is the entry point of subroutine F. So we have line 16 here. The 3 items that we have here will still be there on the stack. So we still have 6, 5, and also the return address. But at this point, I'm pushing EBP on the stack. And that's why the old value of EBP is also pushed on the stack at this point, and the stack pointer is pointing at this particular item right after line 16. Are we doing okay so far? Okay. And then after this point, with line 17, the line 17 is a little bit hard to represent because it doesn't really change anything on the stack. Instead, it's making a duplicate pointer of the stack pointer. So as far as you can see, there's no change at all on the stack. The stack pointer is still pointing at old EBP, but at this point we have a different pointer that is also pointing at old EBP. I'm trying to find a way to represent the fact that we have 2 things pointing at the same location. So what I'll do is I'm going to use the background color to indicate what EBP is pointing at, and then use the rectangle to represent what ESP is pointing at. Okay, so this way I can have independent ways of looking at things. So I'm going to use a slight, beige-ish, yellowish color. Does it show on the projector?
Yeah.
Okay. Yep. Mm-hmm.
Before you set old EBP to 0, could you set it the label?
Right.
Yeah. Could you set it to the address of EBP?
No, you cannot, because this is all floating. In other words, if you have a recursive subroutine, then the value of EBP or the offset, the absolute address of where you store old EBP will change. Because the stack pointer, the value of the stack pointer at the entry point of a subroutine cannot be predicted. And that's why you cannot use an absolute address for EBP. It has to be relative to what EBP itself is pointing at. But old EBP itself is really nothing more than a snapshot of the stack pointer after the push out instruction. So now we have 2 things pointing at the very same location. And then on line 18, okay, so we'll go ahead and split the column so we can see different things at the same time. So this is the end of line 18. Line 18 is changing the stack pointer, but not the frame pointer or ESP. So the stack still has the same content: E6, 5, the return address, old EBP, and some junk here. Okay. But if you look at the pointers, the stack pointer will now be pointing at this location. So this will be there'll be a rectangle around it because this is what the stack pointer is pointing at. The frame pointer EBP is still pointing here. So now we start to see how the 2 pointers are working, because one is still pointing to the same place and the other one is floating. Are we doing okay so far? Okay. And then we look at line 20, line 21, and line 22. Now, line 20 and line 21 really do not give us anything that we can see on the stack. So I'm not going to trace those 2. But line 22 does something to something that is on the stack. All right, so let's see what it is going to do on the stack. 6, 5, the two parameters are still there. The return address is still there. Old EBP is still there. But what it is changing is this location, because it's changing the location that is 4 bytes below where EBP points to. EBP is still pointing to the same location because I have not changed EBP itself. So EBP is still pointing to the very same location as last time, as the previous column. But 4 bytes below that, where ESP is pointing at right now, is going to store the sum of x plus y. And this is what the stack pointer is pointing at. Is that okay? Does everybody understand, how I store the sum of the two parameters? I think I changed that, so it has to be subtraction, I think. So it's x minus y, not x plus y. But that part is not important because I'm mostly using this as an example to illustrate how the stack is being used. Is that okay so far? Okay. Line 24 doesn't do anything to the stack. I'm not going to trace it, in this particular trace. And then on line 26 is reversing what line 17 did. In other words, I'm moving EBP back to ESP. So that means, both will be pointing to this location again. The content of the stack is not changing. So we still have all of these things on the stack, just like that. And technically speaking, this is still there on the stack, but anything that is below where the stack point is pointing at is subject to change without your knowledge. Okay, so I can no longer count on x minus y still being there. So I'm not going to say anything about this location. The most important part is at this point we have both of those pointers pointing back to this location. In other words, it is both pointed to by the stack pointer and also by the frame pointer at this point. Are we doing okay so far? And this is line 26. On line 27, okay, this is line 27. Line 27 is going to pop into EBP. In other words, it's taking whatever the stack pointer is pointing at, which is old EBP, and store that into EBP. So it is doing two things at once. One, it is going to move the stack pointer, because every time you pop something, the stack pointer points to a higher location after that. So that's the first pointer that got changed. The second thing is changing is EBP itself, because it's restoring the value of EBP back to the value when I first got control in the subroutine. I have no idea how my caller was using EBP, so I can no longer highlight something in yellow to indicate what EBP is pointing at, because it can be used for whatever purpose that my caller wants to use it for. So that's why the column in this case, we still have 6, 5, as our parameter. The return address is still here, but this becomes what ESP points to, because of the pop instruction. It's moving the stack pointer back to here. So we go to borders and just highlight it with a circle, with a rectangle. And we lose the yellow background because we have no idea what EBP is pointing at this point. Is that okay? Now that we are done with this step, after line 27, we have line 28. Line 28 is a return instruction. The return instruction also has two individual operations built into it. The first one is to pop whatever the stack pointer is pointing at this point, and then the second thing is to continue execution at that location. Okay, whatever you pop from the stack will be an address, and it will continue execution at that address. So in this case, what it is going to do is to utilize this return address here, and basically continue execution at that address. But at the same time, the stack pointer will also be moved because you're also doing an implicit pop operation. So the 6 will still be here, the 5 will still be here, but the stack pointer will now be pointing at the 5 and not the return address anymore. Just like that. And because it is also continuing execution at return address, that will be the instruction right after the call instruction. So that will be line 42. And on line 42, it is just adding 8 to ESP. So now ESP will point back to whatever is before the 5 and the 6. And in this chart, it's not displayed. So the stack pointer is will now be pointing to whatever is above the 6 or row 2 in this case. Is this helpful? I mean, a little bit. Okay. So you have to kind of combine the implementation in assembly with the chart here to kind of visualize, what is happening on the stack. Things getting added to the stack, pointers being changed, and then reversing all those operations at the end of the subroutine. Any questions about this? What if in a subroutine, for whatever reason, you accidentally change the return pointer? Just think about it, okay? Because everything is on the stack, and the stack is modifiable by your code, okay? So you can easily do a move instruction, an add instruction, or whatever to the return address that is on the stack. What happens when you mess around with the return address? What would be the symptom of something like that? You can, okay, if you're lucky, you get a sex fault. Okay? If you modify the return address to an address that you're not supposed to go to continue execution, you get a segmentation fault. But that would be a lucky case because because the problem occurs immediately after you try to do a return instruction. Okay? If you're not so lucky, then you'll be modifying like the least significant byte of the return address. So as a whole, the return address is still a valid address within your program. It's just not where it is supposed to go.
So we'll just start executing some random function.
Yeah, if you're unlucky. Yeah. If you're lucky, in that case, it will be in the middle of a valid instruction. So it will still be, it's still possible to interpret that byte sequence as an invalid instruction and therefore still give you a segmentation fault. But if you're very, very unlucky, it will land at a spot where it is actually a legal instruction and will just continue execution at that point. In other words, you can basically experience what we, if you can do, I still remember the opening ceremony of this class where I gave you a program and I said, it will go to a subroutine, but it will return to something else. That's exactly what can happen here. Okay, yep.
In GDB, can you single step to find out where it's going?
In GDB, yes, you can. So that would be a good place to put a breakpoint is at the return instruction. So you put a breakpoint at the return instruction, and then you can just kind of, right at that point, I would not, if you suspect something is wrong at that point, I won't even single step. I would just go through the stack and look at what the stack pointer is pointing at, and also the content at that location before you even single step the return instruction. So those would be critical places because that's one instruction that can cause a segmentation fault. Okay? So that's one thing that can mess up. Okay, you can mess up the return address. What if your subroutine messes up ODBP? Now, in this case, subroutine F, if I have a bug in subroutine F and somehow it messes up ODBP, what do you think would be this, a possible symptom of this kind of problem? It won't happen in F itself, okay? Because it is the caller of F that will be utilizing the new value of EBP, okay? Now, most likely than not, the caller is only using EBP just like a frame pointer for that particular invocation. If you're lucky, OEBP will be pointing to some really random place and it will just, bam, it stops, okay? If you're not lucky, OEBP will be off by just a few bytes, okay? And then the caller of this subroutine, in this case, G, will be accessing its own local variables and parameters in the wrong way. It's using the wrong part of the stack as the frame, which is really bad. Because it won't cause any symptoms until it gets to its own return. And then most likely than not, the return address, because it's at the wrong place, will cause a segmentation fault when it tries to return. Okay, so we are looking at segmentation fault and other types of symptoms that are delayed. Okay, it's not going to happen right where the problem is. It will occur later, and that's why when you debug programs like this, you have to focus on the stack pointer for one thing, and also what the stack pointer is pointing at. Because it is possible that the stack pointer itself is okay, it's pointing at the right location, but the location itself is corrupted, so it doesn't have the right value at that point anymore. Is that okay? So at this point, we don't know what kind of code in C can possibly cause these type of corruption. We know how we can do it in assembly, right? We just mess up the wrong part of the stack and things this bad can happen. But how can this kind of thing happen in the C program? We have not talked about how to do addressing in array indexing, and that's basically the biggest danger when you write programs in C, and that's the #1 reason why people can corrupt the stack or portions of the stack. All right. So is this helping a little bit with your homework assignment? Because your homework assignment has pretty much the same kind of elements. Okay. All right. So I'll just kind of keep these documents up. Well, maybe save it. So this is the spreadsheet is called stack trace, and then the document itself is, let's call that stack trace.code, okay? Because that's the code of the stack trace program. All right, so now we have those saved. Take them out. I'm going to skip the last portion of returning a value. Okay, let me just kind of scroll all the way back down to the topic here. If you look at this particular topic, it will talk about how to return a structure. But I want to talk about what a structure is and how to represent a structure before we get back to here to talk about how to return a structure. Okay, so I'm going to skip it for the time being. Move on to the next topic, and then we'll come back here once we talk about what the structure is and how it is represented in an assembly language program. So now I'm moving on to topic 10 to talk about just regular data structure or struct in C or class in C++. Brings me to the same portion. Okay, data structure. All right, so we'll start with something that's simple like pointers, and then we'll kind of progress and talk about array indexing, and then we'll move on to structures and so on and so forth. Okay, let's deal with pointers first. And the best way the way I usually do this is I will use a program to kind of demonstrate how to do it, because once you look at the program, it becomes kind of obvious. It's better than me just explaining it in text. We'll go ahead and write a program in C, and then we'll translate that into assembly, just like usual. But we'll go ahead and implement swap. Okay, the logic of swapping. Does anyone still remember how to do the swap logic in C or C++? Not using passing by reference, but using pointers.
Create a temporary variable.
Yep. Okay. Well, first of all, we need two parameters, right? We need two pointers. One pointing to the first thing. Okay, we'll just say this is a pointer to an integer, we call it x, and this is another pointer pointing to another integer y. Inside the subroutine, you have a temporary variable, we just call it t. So t has to remember what p used to point to, and then you can update what p used to point to what y points to, and then you can change what y points to what the old value of what what x points to. T like that. Okay, so that's the usual code to do value exchange of two variables written in C. Okay. Are there any questions about this? I trust that everybody knows what a pointer is in C. Because there was one time when I got a prerequisite challenge from a student who said he had taken Java and would like to have that to be considered equivalent of C and C++. And against my better judgment, somebody signed off the prerequisite challenge. I cannot sign prerequisite challenge to my own courses. Okay, and that student, once we got to the pointers, that student was like completely lost because there's no such concept as a pointer in Java. Okay, so assuming we already know what a pointer is, let's go ahead and implement the code for this particular subroutine. First of all, we go through the same motion. Old EBP is 0 because EBP points to old EBP, and therefore the displacement to old EBP is 0. Return address is old EBP plus 4, and then we have PX, which is a pointer. It is return address plus 4, and then PY is PX plus 4 because as a pointer, it only takes up 4 bytes in a 32-bit architecture. And then we have our local variable t. T is old EBP minus 4, which is the size of t. And our last local variable is t. So this way, in my assembly code in the subroutine, I can use just last local variable in case I need to add any additional local variable. I don't need to change the code itself. I just need to change the declaration of the labels. Right. So into the subroutine. Okay. So here we are writing the subroutine. The entry code is always the same. Push EBP, move L, ESP to EBP, and add long last local variable to ESP. The exit code is always the same. Move EBP to ESP, pop L, EBP, and then return. So now I'm ready to put all the code in between. The first one is to go to whatever PX points to, and then copy that to variable t. All right, so how am I going to do that? Okay, let me write this first, and then you guys can tell me, what is wrong with it and how to fix it. Okay, so you already know this code is incorrect. Move L, P, X, EBP to a register because I cannot do a memory-to-memory transfer.
Move the window.
Sorry?
Can you move the window up?
Oh, sure. And then I move EAX to my local variable t, like that. Okay. What is wrong with this code? What is being copied to my local variable t in this case? Am I copying the pointer, or am I copying what the pointer points to? What is on the stack, by the way? What is pushed on the stack as a parameter? According to, okay, let me just make this a little bigger so we can see both the C code and the assembly code. Or better yet, I can do this. Okay, so I can look at the C code up here, and then look at the assembly code down there. So what do you think is pushed on the stack by the caller? Is the caller pushing 2 integers, or is the caller pushing 2 pointers to integers? Pointers to integers, okay? So that means, at px many bytes off from what EBP points to is the address of an integer. Same thing applies to py. Okay? So when you look at the assembly code, what this instruction is doing is really copying the pointer into EAX, but not what the pointer points to into EAX. So if I want to make this really clear, I'm going to write some comments here, and then I'll say, EAX now points to an integer. So the second instruction, the way it is written here, is going to copy just the pointer itself to local variable t, but not as the C code specifies, where it has to copy what the pointer points to variable t. So how do I fix this? I need one more instruction to finish this particular operation in between the two that I already have. What should I put here? I need something to do a dereference. And the way to do it is the parentheses, indirect addressing mode. Okay, and you can do this too. And you can use the same register as both the source and the destination operand, because what this instruction will do is first to use EAX to do the dereferencing, and then after the dereferencing, the result or the value is stored somewhere that is not named, and therefore we can copy that in return to EAX. So that's what we need to do with the first line in the subroutine swap. So now once you understand how this works, the second line is kind of the same thing, except we have to store directly to where PX points to. So the second instruction, okay, let's do it this way. Let's do it, in a way that's kind of interesting, just to combine things that we know already. So EAX now points to integer because we are moving just another pointer into EAX. But this time I'm going to do something like this, which is something that you can only do with a cisp architecture, because it's really combining a whole bunch of operations into one single instruction. Because what this will do is it will first do a dereference of EAX. In other words, it goes to where EAX points to and retrieve those 4 bytes. And then it will push those 4 bytes on the stack. Okay, I'm saving it on the stack so I can later on pop it into somewhere else. Is that making any sense? Okay. So my next instruction is to do something like this, with PX. So I'll copy PX, which is a pointer, into EAX. EAX is now PX, and then I'll do a pop instruction here, except I'll pop it to whatever EAX points to at that point. But between the push and the pop, I changed EAX. So this is not a useless operation, because I use one location to supply the 4 bytes to push on the stack. But when I'm popping, EAX has changed already, and I'm popping it into a different location. Is that okay? I mean, or do you guys want to kind of slow down and kind of digest these instructions?
I just don't understand the last one just did.
Okay, well, let's give them line numbers first, and then so we can refer to each individual instruction by line. Okay, let's do with it line by line. Line 25, is that one okay? We are moving a pointer into EAX. So EAX is a pointer to some other location that has an integer. Is that good? Okay, because that's the same thing as the previous set of instructions. Line 26, is that okay? Line 26 will use EAX to go to some location in memory, retrieve 4 bytes from that location, and then it will push those 4 bytes on the stack.
So it's storing the data, not the address?
It is, say that again?
It's not storing the address, it's storing the actual values.
It is because because the operand to push is a indirect operand. So it is going to do a dereference before it pushes. Is that okay? All right. So line 27, basically the same thing as line 25, except this time I'm initializing EAX to a different pointer, the destination pointer, so to speak. And then on line 28, it is doing a pop. In other words, it is going to the stack and say, okay, what did I just push? Like 2 instructions earlier. Okay, that's basically what PY was pointing at. Okay, not PY, but what PY was pointing at is what the stack pointer is pointing at. And I'm going to pop those 4 bytes to whatever EAX is now pointing at. But what EAX is pointing at is the destination where I'm supposed to store the result. So that's how these 4 instructions work. There are numerous other ways to implement exactly the same thing, but the use of push and pop is really handy because I don't have to use another register to store the value. Yep.
So lines 25 through 28 are essentially
star PX equals star PY. Yep. So let's turn on line numbering in this window also. And yes, VI is really nice because you can split the screen and do this kind of thing. Are there any other questions? No other questions? All right, let's move on to the last line, line 6 of the C code. So line 6 of the C code is really kind of like a combination of line 4 and line 5. Okay. We can do the same thing as before. In other words, we can put our local variable t on the stack first, and then we can move py EBP into a register, because you can only do indirect access through a register, and that's why we have to put that into a register first. And then we can just do a pop L to whatever EAX points to, and it's done. So in this case, line 30, 31, and 32 will implement what line 6 is trying to do in C. Okay. Is that okay? The push and the pop is really just so that I can say I don't have to use up another register. I could have done that using another register, but this is really just kind of handy for that purpose. But the key is the use of the indirect addressing mode at the right moment. Any questions about how pointers are implemented or utilized in assembly language programming? Is that okay? All right. Let's make this program a little bit longer by also including the caller, because this is what the callee or the subroutine being called is seeing in terms of having a parameter that is pointed to an integer. So how do we call a subroutine like this in C? Okay, so let's deal with the C version first, and then we'll deal with the assembly version. So let's say we have a G subroutine here that doesn't do anything except to test my code here. So in G, I would have two local variables. Let's call those A and B. And I'm not even going to bother to initialize A and B because I'm focusing on just how do we call a subroutine like this? Okay. How do I call swap in this case? Can I just say AB like that? No, because the compiler is going to complain because I'm supposed to supply a pointer or an address of an integer to px and also an address of an integer to py. And the way it is specified here is they are just integers. They are not an address to an integer. So what we need to do is to use the ampersand here, which means I'm using the address of A and the address of B. Okay, so that's the proper way of calling swap from the perspective of the caller. Okay. The question now is, how do I implement that in assembly? Okay. So let's switch to the assembly version here, and we'll deal with G. And this is the reason why I like to use one subroutine per file, so I won't end up with a chance of reusing the same label. And that's also why I have to use A and B and not X, Y. Well, I guess PX and PY would be different, but I cannot use T because T is a local variable in the other subroutine. But at least in this case, I'm not using the same label, so I can actually just continue to do it kind of the same way. So in this case, I have this really belongs to another file, okay? But I'm going to put it into the same file just so that we can see it. So I'll just put a comment here and say this really belongs to another file. Okay. So with that in mind, we can just go ahead and assume that this is another file only for subroutine G. So we'll redefine OEBP equals 0. Return address is OEBP plus 4. And then we have no parameter on that side, so actually return address doesn't need to be named because we don't have any parameters. But we do have two local variables. So we now have B is being a local variable, is OEBP minus 4, A is B minus 4, and then my last local variable is A. The entry point, the entry code and the exit code of G is identical to the entry code and the exit code of swap. In other words, we have to do the same thing, which is push EBP, move ESP to EBP to take a snapshot of the stack pointer. And then the exit code is, forgot one thing here, add long dollar last local variable to the stack pointer to reserve the space for my local variables. The exit code is exactly the opposite of line 55 and line 56. We restore the stack pointer from the frame pointer, and then we restore the frame pointer from what the stack pointer is pointing at, and then we can return at that point. So you can see that the entry point and the exit code are basically the same as the other subroutine. What is different is in between. Okay, in this case, we just have to call swap. So that part is easy. Okay, calling swap is easy. But how do we set up the parameters? So I'm going to write some code that is incorrect, and you guys can tell me why it is incorrect. Then we'll try to figure out how to do what is the correct thing to do. So we know we have to push the last parameter first. In this case, the address of B is the last parameter, and then the address of A is the second parameter. And we also know that each address is going to take up 4 bytes. So when swap returns, I have to reclaim up to 8, in this case, exactly 8 bytes. So we just need to add 8 to ESP to reclaim all that space. But this code is incorrect because it is not pushing the right things on the stack as parameters. What is this actually pushing on the stack?
The values themselves.
The values, okay, is pushing the value of local variable B and the value of local variable A on the stack, and they are not addresses of those local variables. Now how do I fix this problem? There are many, many ways to push the address of local variable B on the stack. Okay, let's do it the slower way first, and then we'll try to use some kind of trickier way but shorter way to do it. The slower way to do this is to say, okay, whatever I have to push on the stack, I'm going to use EAX to do the calculation first. Okay? And I know the address of B is somewhere close to what EBP is pointing. Okay, so the first thing I do is I'm making a copy of EBP into EAX, because I know EAX now at this point is close to the address of B, but not quite there. Okay? What do you think I have to do to make EAX the address of local variable B? What is the label B? What is the meaning of the label B in the assembly version of this code? It's the offset of local variable B from where EBP points to. So if I start with what EBP points to, which is now in EAX, what do I need to do to it in order to make it the address of local variable B? Just add the label B. Okay? So we just have to add the label B, which is $B in this case, to EAX. At this point, EAX is the address of local variable B, and I can just push it on the stack. In other words, line 59 to 61, those 3 instructions, is going to push the address of local variable B on the stack. And you can do the same thing with local variable A. But instead of doing the same thing for local variable A, I'll show you a slightly different way of doing it, which is kind of tricky and not any more efficient, but nonetheless, it does give you an exercise of understanding the instructions and actually understanding how we can combine stack operations with other operations. So the second version, or when we push the address of A, I'm going to do something like this. I'm pushing EBP on the stack first, and then do an add L, $A, which is kind of the same thing as last time, but I'm doing it to whatever the stack pointer is pointing at that point. So let me just put some spaces around it so we can see more clearly which code we are talking about. So I'm now claiming that line 63 and line 64 will push the address of local variable A on the stack. And it's doing that without using an additional register. Is that making any sense or not? Line 63 is pushing EBP on the stack. Okay, so whatever is on the stack after line 63 is close to pointing to my local variable A. Not quite there, but close. Line 64 is adding a very small offset. Okay, in this case, I think it's -8 to whatever the stack pointer is pointing at. What is the stack pointer pointing at? EBP, right? The value of EBP. So at this point, I'm just messing around with whatever I just pushed on the stack to turn those 4 bytes into the address of local variable A. Now I have to point out that the first sequence, line 59, 60, and 61, is actually slightly more effective or more efficient compared to line 63 and line 64. Line 63 and line 64, that's right. The reason has to do with line 63 and line 64. They involve a lot of stack-based operations or memory operations. Whereas if you look at lines 59, 60, and 61, there's only one memory operand or implied memory operand, which is the push instruction. The push instruction has to push something on the stack, and therefore there's always an implicit memory operand in the push instruction. When you look at line 63 has one memory operation to push something. Line 64 has another memory operation, so it has 2 memory operations as opposed to 1 in the other sequence of operation. So when you look for efficiency, the first one is better. The second one is kind of a neat way of doing things, but it's not any more efficient than the first one. It's actually worse than the first one.
Could you explain line 64? What exactly is doing with the ESP?
It is adding 4. I mean, it's adding effectively -8 because of $A, or the label A is -8, so $A is basically the immediate operand of -8. So it's adding -8 or subtracting 8, if you will, from what ESP is pointing at. Because in parentheses, ESP means indirect operand. So it's basically using ESP as a pointer and using that as the destination address. But what does ESP point to? ESP points to the very last thing that I pushed on the stack, right? What did I push on the stack? EBP. In other words, I'm adding -8 to EBP, but everything is done on the stack itself.
So you're allocating.
I'm not adding. I have to do a correction first. I'm not adding 8 to EBP. I'm adding 8 to a copy of EBP. Go ahead. That copy is
I'm
on the
not
stack.
quite sure. I'm still not quite sure what you're doing. Could you draw it out or something?
I'm trying to push the address of A on the stack because swap as a subroutine is expecting the address of an integer.
I don't see how you're pushing 4 bytes on the stack.
Push EBP is going to push 4 bytes. And EBP being the frame pointer is pointing at a certain place that is fixed within this call frame. Okay. But it's not pointing at the local variable that I want to, that I want the parameter to point to. So I have to add a small displacement or offset to a copy of EBP so that it is going to point to the location that I want it to point to.
But isn't A above EBP?
No, it is below because A and B are local variables. So in terms of their address, they're both below OEBP. Because the allocation of A and B are done after we copy ESP to EBP, and that's why they have a lower address than OEBP. Sorry.
When you add A to ESP, how do you know that offset, that value of A will make it completely pointing at A?
You set it up that way. Scroll up so that you can see where you declared, like, let's say the percent on the top line. So it's supposed to
The reservation of the local variables is done by line 57. And line 57, in return, uses the label last local var to tell me how many bytes I'm supposed to allocate. So effectively, because ODB is at 0, right? So B is -4, and A is -8. I'm adding -8 to ESP, which effectively lower the ESP by 8 bytes. Okay, and therefore I'm reserving 8 bytes.
Okay.
EBP still points to the same place. It's just that below where EBP points to, I have 8 bytes that other things cannot touch. That I'm going to use those 8 bytes for my local variables.
So you could have just said add L $-4.
Twice. I have to do that twice.
Or -8.
Yes.
Okay.
But the use of of symbols make it less sensitive. If I have to add additional local variables, I only have to change the declaration of the symbols, and I don't have to touch anything within the subroutine itself. So I don't have to worry about, oh, I'm using A in this case. What if I want to define another local variable before A? Okay, so I can handle all of that stuff using the symbol definition, but not having to mess around within the subroutine itself. But we're still doing okay so far with this particular program, how to pass the address of a local variable to another subroutine. Yep.
What's the point of on line 63? What's the point of pushing EBP on the stack?
Because I have to push the address of A on the stack anyway, so I'm just pushing something that is close to that address on the stack first, and then I complete the calculation on the stack using the add long instruction on line 64. In other words, if you look at the first sequence of code from line 59 to line 61, it finishes all the calculations first, and then they push the final product on the stack. When you look at line 63 and line 64, it pushes a partial answer onto the stack first, and then it finishes the calculation on the stack using ESP, as a pointer to the result, on the stack. So that's the only difference between these two sequences of code. One is doing the calculation in the register and then push the register on the stack. The other one pushes a value that's close to what we want on the stack and then finish the operation on the stack. Is that all right? Because I want to expose you guys to different ways of doing the same thing, because this is a really good way of looking at the two solutions, the first chunk of code from line 59 to line 61, and the second chunk of code of line 63 to line 64, and basically see that they are doing pretty much the same thing, but in different ways. And that's, I think that's a good exposure, because now it helps to kind of reinforce your understanding of the addressing modes and also the instructions. Because we have not been using any type of really exotic or new instructions. We're still using the same old instructions. It's just that the combination of the addressing modes and the instructions makes it kind of interesting. Yep, go ahead.
Could you do a drawing anyway?
I can try, because it's. I can execute a code too. I mean, if that will help.
I think misunderstanding is what you're doing with the variables when you set them up before. So the idea that you're using A is not anything other than just an offset. You conveniently set
Yeah, the
up.
label A
Yeah.
is an offset to the local variable A in C, and then the label B, the same thing, is an offset to the local variable B from
And-
where EBP points to.
And line 63 has the upside of moving the stack pointer to whatever you just pointed on it, which is EBP, or whatever you just pushed onto it, which is EBP.
Correct.
Which then is what allows the second line to get to that and apply
Right.
the offset.
Okay, so I'm going to do this on the whiteboard. So I'm kind of, so people who are not physically here, will probably kind of suffer a little bit because they're not physically here and actually see the whiteboard. But I'm not doing this intentionally. I'm doing this to answer your question, and this is the more effective way of doing it. Okay, so let's take a look at the stack, from the beginning. Okay, so from the beginning, what we have is the caller always has a return address on the stack, and this one is not. Okay, this is better. Okay, so the return address is pushed by the caller. Okay, it's not up to the subroutine to control. So this is not because of swap; it's because of the caller swap. Okay. No, I take it back. This is G. Okay, so we're talking about subroutine G. This is before subroutine G gets any control. When subroutine G gets control on line 55, we have pushed EBP. So now we have old EBP on the stack. Okay, I'm saving this so I can restore EBP later on. And then on line 56, we are making a copy so that EBP now points to the very same location here. So at this point we have EBP and also ESP pointing to the very same location. Are we still doing okay so far? This is the result after line 56. On line 57, we are basically reserving 8 bytes, but because we are looking at the 4-byte chunks in this case, I will just reserve 2 more items because each item is a 4-byte thing. So at this point, ESP is now lower to point to, basically this is our local variable A and this is our local variable B. Are we still doing okay so far with this picture? Now, it is very important to understand that in assembly code, the label A is not referring to the value of local variable A, but it is referring to this distance here. That's really our label A because it's -8. It is 8 bytes below where EBP points to. And label B is the displacement or the offset from EBP points to the first byte of local variable B. So it is very important to remember the labels are now becoming offsets and not the actual variable in C. Are we doing okay? All right. So we can skip line 59 to 61 because I don't think you guys have any questions about that. Or should I trace that too? That one is okay? Okay. So we'll move on. Okay. So after that, we will have the address of A pushed, the address of B pushed on the stack. Because that's what line 59 to 61 will do. Okay. So after that, ESP is now running here. Right? Okay, so we are now ready for line 63. What line 63 is going to do is it's pushing EBP on the stack. And then the stack pointer is lowered to point to the very same location. Are we doing okay so far?
Does it move the EBP pointer?
No. It is making a copy of EBP to here. So technically speaking, this is where things can get a little bit difficult to understand, is that these 4 bytes on the stack is actually a pointer that is pointing to its location. It's basically a clone of EBP itself. Is that okay? So the red dotted line is really just saying, okay, we can treat these 4 bytes as a pointer, and that is where it's pointing at, which is old EBP, because it really is just a copy of EBP at this point. Okay? Line 64 is going to add $A, which is basically -8, to whatever the stack pointer is pointing at. Okay? So at that point, let's hope this blue one is working. So at that point, this is no longer EBP, but it's EBP -8. As EBP -8, it is no longer pointing to this location. It is now pointing at this location. And therefore, it becomes the same thing as the address of A. Is that okay? This is why I can't do it with a spreadsheet, because it has a lot of things other than items on the stack that I have to represent. Is that okay? It takes some getting used to. You basically have to look at the code and draw your own picture. Not referring to mine, and draw your own picture. Then you will start to kind of absorb that information. All right. So we are doing okay so far with taking the address of something and then pass that on the stack. Okay. Well, that takes care of 16.1. Now we can go ahead and talk about 16.2. How do we deal with arrays in assembly language programming? That's smart, taking a picture of that. As I said, I'm going to get an Elmo and use that so I can just use a piece of paper. It actually took me a little bit of time to find a easy solution, because I've been thinking, using, yeah, go ahead.
picture like he is and then put it in the comments or the description of the YouTube.
I could send
But
it to
ultimately,
you.
Well, you guys
I
can
see
send
the
it to me.
process
I can
of
send
going
it
through
through.
it.
Mm-hmm.
Because I mean, we didn't. This is just the final results. But
Yeah.
Right, it is the animation that is actually kind of
You wanna
important
go
to.
through that again? I'll actually record video.
You could also get a tablet for the computer.
Mm-hmm.
oh,
Well, I was thinking about all these complicated solutions. Getting a Samsung Note, 8, the 8-inch Note or the 10.1-inch Note, or getting
oh no, he meant like
a Live Scribe.
Yeah, that thing. Yeah.
And then it just occurred to me, well, I can just use a webcam and stare at a small, whiteboard. Then I can do everything on the regular whiteboard and have the webcam to capture it. And because everything on the screen is already screen captured, so if I put the display of what the webcam is seeing on the screen, that too will be recorded automatically. So then you have the entire full sequence of all the editing, all the erasing of the pointers and whatnot, also captured. So that turned out to be the easiest solution. That's also the least expensive because a webcam is inexpensive, cheap. How much is a webcam now? I just need 1024 by 768 because that's the resolution that I'm capturing. It doesn't matter if the webcam itself is 1080p because it's not going to get recorded in 1080p. So how much is a 1024 by 768 webcam?
$10.
If I can buy one.
$10.
$10, yeah. And the only problem with that approach is there has to be enough light. So I might need a little extra lamp to kind of shine on that piece of paper. And that's another $5.
That might be more expensive than
Sad.
Okay, so but the whole point is it's still eventually you can look at the instruction and actually go through these calculations in your mind and figure out what the instructions are doing. But initially having this picture would be helpful. All right, any questions? Let's move on to, yep.
Yeah, I just realized when you push EBP onto the stack and then you moved the address there, doesn't that overwrite the old EBP?
No, the old EPP is still here.
No, I mean the one that pushed on the stack before. That one.
You mean this one?
Yeah.
But this
Yeah.
is not a registered EBP. I'm copying the registered EBP to here so that it effectively points to the same location initially. And then I subtract 8 from it, so now it points to this location. In other words, whatever I do to these 4 locations on the stack has nothing to do with EBP itself. Because I'm doing it to a clone of EBP, which is on the stack. Okay? And that's why the stack is so useful, because you can do all sorts of stuff, on the stack, and then later on just erase it. It's kind of like a whiteboard. But you have to follow the last in first out order in that case. Like just randomly erase something. All right, so let's go to arrays, and the first part is the concept of an array. I hope you guys still remember restrictions of arrays in C. Okay, so can someone tell me what are the at least 2 big restrictions of arrays in C?
Contiguous memory.
Well, it has to be contiguous.
All same type.
Go ahead.
All the elements must be the same data type.
Okay, and therefore they all have the same size. Okay, and the last restriction has to do with when you declare an array, something has to be right. The size has to be known when you declare the size of an array. You cannot make it longer or shorter, after that. Okay, very good. So what we'll do now is to look at some of the typical operations that you want to do with an array. The first part is how do we allocate an array in assembly code? Okay. So if this is not needed anymore, I'm going to save it and get out of this one, and we'll go ahead and start with an array program. And I think I can only get through maybe a small portion of arrays today, but we'll go ahead and finish as much as we can. So we have an array A, and we'll make it, I don't know, 25 elements long. Okay, so this is all that I want to do. How do we do something like this in assembly code? Well, in assembly code, we still have the same stuff here. OEBP equals 0, and then we have return address is OEBP plus 4. But since A is a local variable, it is on the negative side. So the question now is, I know A is old EBP, which is 0, minus the size of A itself. But how do I do this calculation in assembly code? Well, the size of an int with a 32-bit architecture is assumed to be 4 bytes. If I want to remove that ambiguity, what I need to do is to go here and say it's int32_t. Then we know for sure that each element in array A is exactly 4 bytes long. So knowing that and knowing that we have 25 of those things, how many bytes eventually do I need to allocate? 100 bytes, okay? So I could just say, oh, we have 100 bytes here. But I would not do that. Instead I would do something that's a little bit more kind of symbolic. So I would say, int 32 size is 4. And then I would say, this is 25 times int 32_size. I know in this case it seems like a waste of one line, and some label definition, because why do we even bother to do this? Because int32 clearly indicates that the width is 32-bit or 4 bytes. Well, it's a habit kind of thing. Okay, once you get into the habit of using a symbolic name for the size of something, it does make your program more manageable down the line. If I do 25 times 4, it's better than just 100, because if I say 100. 2 weeks later, I look at the same code and I go like, why am I allocating 100 bytes here? What does that mean? Okay, but if I do it this way, it is very clear that I'm allocating I'm allocating space for 25 32-bit integers. It becomes very clear, not 100 chars or anything like that. And to do the allocation, it's the same thing as we always do. Okay. So when you look at the entry code of F, it's the same thing. Push EBP, move ESP to EBP, and then add long. Okay, I forgot this last thing here. Last local variable is A in this case because we only have one local variable. So add long $last local variable to ESP, and then the exit code is basically the same thing as before. EBP, ESP, swap the order because we are restoring the stack pointer from the frame pointer. Pop out EBP to restore the old value of EBP, and then do a return. That's it. It's no different from a normal local variable, except when you calculate the size of the array, you have to multiply the number of items in the array by the size of each item in the array. Okay? So that really is the easy part of handling arrays. The difficult or slightly more difficult part is how do we get to a particular element? How do we get to the value of an element in an array? And then how do we compute the address of that element in an array? Okay. And this is also a good time to demonstrate how array indexing can easily mess up the frame, can easily mess up other items on the stack. Because all you have to do is to supply the wrong index to an indexing operation, and then you will be accessing other stuff on the stack that you're not supposed to access. Okay. So I'll stop here today, and you should read ahead of me to understand how arrays are implemented in assembly. And then next time we'll deal with all the dangerous operations that you can do with array indexing. Homework is due on the 30th,
It took me a while.
which is next Tuesday.
It's like,
So you can that can help ruin your entire weekend.